This section of slides is going to go from 27 to 36 in the carboxylic acid and derivatives chapter. And this portion will cover esters. This again will largely use the 1,2 addition mechanism to transcribe an ester or to change an ester into another functionality. Again, esters, if you recall reactivity, right, are on the lower end of reactivity. When we think about reactivity, we see acid chlorides as very, very reactive to nucleophiles attacking, followed by aldehydes, followed by ketones, followed by carboxylic acids, and esters, which are about the same reactivity-wise. So carboxylic acids and esters are relatively similar. Therefore, you're going to see a lot of acid catalysis or strong bases used in order to get them to react. Unlike the previous section that we just discussed, we don't have a really strong leaving group, and also converse to having a chlorine, which is an electron withdrawing group, right? It's withdrawing. We have an oxygen, which is donating. Therefore, this is contributing to the electron density at the carbonyl and making it less reactive. So esters, it's kind of worth noting. I think it's kind of interesting because because of their low reactivity, kind of like an amide, right? Remember that amides are even lower in reactivity, and amides play a large role in biochemistry because this bond, as I'm pointing out right there, is the peptide bond. So they're stable. Esters are stable. Carboxylic acids are stable. Amides are stable. Hence, we see them a lot in biological systems. It's also, they're widespread in nature, and often, which I find interesting about them, is that they are responsible for many of the beautiful aromas that we smell. So the scents of a lot of flowers, fruits, a lot of those can be attributed to an ester. They also play a large role in animal biology, and I just think this is hilarious. I've got the moth pheromone shown here on the right-hand side, which happens to be the same pheromone for mating of an elephant. You know, and you just gotta hope that those two species do not exist in the same environment. But it is kind of funny that this moth pheromone and this elephant pheromone are one in the same, right? The elephant sniffing around going, what? I just don't see another elephant, but I'm smelling something. Anyway, transesterification. So now what we're going to do is we're going to just say, how can we convert one ester to something else? And the first thing we're going to do is convert one ester to a different ester. This sounds kind of funny, but it actually serves a very important purpose chemically. How do we do this? No big surprise, we're going to be doing 1,2 additions. So let's say I have methyl ester, and I react it under acidic conditions with ethanol. All right, well, we're driving on the ethanol. Again, notice I'm going back to those reversible arrows, the equilibrium arrows, because I can control whether I want to drive it in one direction or another. So I'm going to drive the alcohol, the ethanol, on, which means I'm going to drive this methyl oxygen off as methanol. And we do this first by activating the carbonyl using acid-base chemistry. Reminding ourselves that the methanol portion is going to be driven off. So this first step was acid-base chemistry, which I probably should have written here to activate. And then the weak nucleophile can do its in and up. This is where I love having my markers because it helps me remember what the heck I'm doing. I'm driving via Le Chatelier's principle. I'm driving the ethanol on. I'm driving what's in yellow off. That's the Q molecule, right? The appendage off the carbonyl that is not a carbon or a hydrogen. That's what's getting driven off. So now it's a little easier to see that this intermediate step of a proton shift helps me clarify which oxygen to put it on. I've got the blue oxygen, I'm driving that one on. I want to drive the yellow one off. So let's shift the proton over so that that is a better leaving group. Remember, driving the ethanol on, driving now what looks like methanol off. I can then use the OH to push the electrons down and drive the oxygen off. Oops. So I drove methanol off and I drove ethanol on. And after all is said and done, I work it up under basic conditions because I was operating under acidic conditions. So to neutralize everything, take off that extra proton. Notice that I have made another ester, but this ester is an ethyl ester when I started with a methyl ester. So you can transesterify an ester to a different type of ester all you want. You just need an acid catalyst and enough of the other alcohol to drive it forwards. This is the type of chemistry that we see in how aspirin works, right? So if you look, you have the arachidonic acid shown on the left-hand side. And in our bodies, this arachidonic acid will interact through an esterification process whereby the alcohol from cyclooxygenase will go in, up, down, out with the carboxylic acid and form an ester. This ultimately produces the prostaglandins, and this is what the response of our body is to if we have inflammation, if we have a headache, right? This is how we want aspirin to work. So prostaglandins have these biological functions, stimulating inflammation and inducing fever. So this is what our body's going to do when we have an injury or something going on. The prostaglandins, the production of these prostaglandins is dependent upon the alcohol interacting with the carboxylic acid and starting this interaction. If we don't want inflammation to occur, if we want to stop inflammation or we want to stop some pain or something from happening in our body, then we need to stop this process. So what happens is aspirin, right, has this ester. If you can see the aspirin ester right here. Here's the ester. And the cyclooxygenase you can think of as your alcohol, your HOR. And all you're doing is transesterifying, right? But you're introducing a better system to sort of distract the cyclooxygenase. We want the cyclooxygenase to stop interacting with the arachidonic acid, and instead we give it a different carbonyl to interact with. So the cyclooxygenase is going to do an in, up, down, out with aspirin, and after it, the group that it's popping off, this is the group that's, I should use my color coding that you guys, we're driving on the acid, we're driving off this OR, this larger OR group, and this is what's making it inactive to causing prostaglandins from occurring in our body and then thus stopping inflammation. So aspirin is really good at doing that, sort of keeping the cyclooxygenase alcohol busy with a different carbonyl. But it's really just an in, up, down, out. It's transesterification. I brought the my alcohol in, and we just had a larger-ish leaving group, right? In with the blue, out with the yellow, from one ester to another. On a side note, this is kind of cool. The OH group of the cyclooxygenase, right, since that's necessary in order for this to happen, the OH needs to react with the carbonyl, right? If you've ever heard, to open a bottle of aspirin and smell it to see if it's still good, this has a lot of truth to it. So old bottles of aspirin, do you know what they smell like? They smell like vinegar. Which is acetic acid. So why should you throw a bottle of aspirin away if it smells like vinegar? Well, here's aspirin. I'm rewriting it. If over time, air and moisture, water, basically just over time, the moisture in the air can actually interact in an in, up, proton shift and down, out. I'm just going to write the down, out for right now. Down and out. And after all is said and done, here is your vinegar. And you popped off the leaving group, which effectively leaves as an alcohol. This will leave, after the proton shift, it will leave as the alcohol. So if water, over time, moisture in the air interacts, it's in the bottle because you have air in the bottle, and it interacts with the carbonyl, then what you're doing is you're popping off the reactive carbonyl that you need in order for the reaction to distract the cyclooxygenase with. And if it smells like vinegar, then that reaction has happened and you no longer have that really important carbonyl there to take over the cyclooxygenase reaction. So you smell vinegar, you don't have the reactive site there anymore. Thus, you can throw that bottle away because you can't perform transesterification. And if you can't do that, it loses its ability as a pharmaceutical. Kind of cool. All right, what else can we do with esters? Well, the most common way to convert an ester to a carboxylic acid is, you can do it under acidic conditions, but the most common way is under basic conditions. And this is also called saponification. Let's do both methods. I am very happy that saponification is the most widely used because these are the easiest to write mechanistically. Here's an ester. Let's do an ethyl ester. If I'm under basic conditions like KOH, the OH minus is strong, and so I am going to do an in and up. Remember, I am driving on the, oops, okay. I am driving, ugh, it thinks I want to open up ChemDraw. Cancel. Okay, I'm driving on the OH. I'm driving off the ethyl portion. Sorry about that. Driving on the OH, driving off the O-ethyl. And I can do my down out just to remember what I'm driving off. Down and out. Now, under these conditions, right, it's not going to stay as the carboxylic acid because I'm working in basic conditions. So understand that under basic conditions, it's going to stay deprotonated, okay, because I have KOH floating around, and this is a carboxylic acid. So it stays deprotonated until you work it up. You need to work it up under acidic conditions to get back to the carboxylic acid, okay? But you know, you're pretty much there once you get to the in, up, down, out. I just want you to understand that you're not completely done. If you're still under basic conditions, it's going to exist as the negative species. And so this will be water soluble. You've really got to add a proton on there to get it back to all covalent bonds and not ionic, therefore making it back into the true carboxylic acid. I just want to point that out. That's really important when you guys did extraction chemistry in the techniques lab. You can do this same reaction under acidic catalysis. Let's do that. Just as you recall, acid-base chemistry and 1,2 additions are much lengthier to write out. But that's okay. We've been doing that pretty much all along. So you start with the ester, let's say methyl ester. We react it with acid and water. We do acid-base chemistry to begin. We need to activate the carbonyl. Now we need to remind ourselves what we're driving on. We're driving the water on. We're driving the methanol, soon to be methanol, off. Now we can do our first in-up reaction. The oxygen goes in and up. Reminding ourselves that we're driving the water on. We're driving the O-methyl off. I'm now ready for a proton shift. Remember, we pepper the mechanism with proton shifts, right? Acid base in up, acid base. Now we're ready for down out. Need to get that leaving group ready to leave. Reminding myself what I'm putting on, what I'm driving off, and now I can do down, out. I'm under acidic conditions, so the carboxylic acid stays overly protonated until I work it up under mildly basic conditions just to get the extra protons removed. And I end at the carboxylic acid, having placed the OH group on and removed methanol as the byproduct. Okay? So that's how you convert an ester to a carboxylic acid. And as I mentioned, carboxylic acids are formed through esters, most often through basic conditions, the first one. And we have a name for it, saponification. And if any of you are familiar with how soap is made, the saponification process is exactly what we just discussed. So I've got here how soap works. Very appropriate for what's going on in the world right now, given that you need to wash really well with soap. You need to create these micelles. Why? Think of soap as this. Oil and dirt and grime is very carbon oily based, right? So water and oil don't mix. So just water on your hands trying to get typical organic grime off of your hands is not going to work out. What you need to do is help like dissolves like. So we need some organic species to help carry it away. So what happens is that soap has a head group or a hydrophilic end. This is the carboxylic acid portion. It's deprotonated, so it's charged and very ionic. Ionic and water loving. And then you have this long greasy tail. Very oily, very water fearing, right? Hydrophobic. These I'm going to represent molecularly as a stick and head. And then when you put them together, like dissolving like, you know, the interactions between one another, they form these things called micelles, where in the middle, all the tails are congregating. And so there's this middle layer of a micelle, which allows dirt to be carried in it. It's sort of like an organic pod, if you will. Micelles we can actually see as bubbles. These are the formation of micelles, these round things that are basically carrying away oily dirt. So recall that soaps are compounds containing a polar group at one end and molecules of nonpolar group on the other end. And the hydrophobic tails, are highly organic, and these surround our oil molecules. So most soaps are produced from fats and oils, which contain 3 ester groups. That's shown here. Here's a typical fat molecule. And if you've heard of soap making, right, they use lye, otherwise known as sodium hydroxide or potassium hydroxide. And this is what does saponification. The OH minus does in, up, down, out, and it ultimately pops a glycerol molecule off. Individually, these are the head groups and the tails, and these are what form the micelles. So the identity of the alkyl chains can vary depending upon the source of your oil or fat, but the concept is absolutely the same from one system to another. And sapo is the Latin word for soap. So hence the word saponification, hence the use of lye in breaking down these fat molecules to create soap, and hence seeing how soap can turn into these globular species, the bubbles effectively, that carry our oily residues away and down the drain. We also had some discussions in class about prodrugs, and esters are another great way to disguise unwanted effects when you're considering drug transport. So drugs that contain hydroxyl groups, like the ones here, are often converted to esters, and this creates a prodrug, right? So as an ester, here are the esters. This is a very thought out, designed system. Why? Well, you're masking the OHs, right? A prodrug form of epinephrine has been developed in which the aromatic hydroxyl groups, the ones in yellow, are acylated to form these esters. This prodrug is called dipivefrin. I'm terrible with names. You guys know that about me already. Dipivefrin hydrochloride. So in this form, the hydrophobic tert-butyl groups enable the compound to cross the nonpolar membrane of the eye. So that's how it gets across. And then once the drug reaches the other side, it's hydrolyzed to release the active drug. So again, hydrolysis is just the reaction of water and acid, or water for that matter. So imagine water being our nucleophile. In this greasier T-butyl form, it can cross the layer, but once it's inside, it can go in and up and down and out, pops that group off, so that you end up with, this carboxylic acid as the byproduct, but the oxygens, those yellow oxygens, stay the same. So you're going in, up, down, and popping this whole large group, the yellow group, off twice. You're doing it twice. And you're revealing the OHs once inside. So this is tricky, right? Making it an ester to get it in there, but esters hydrolyze with water to reveal and cleave off back to their OHs. Esters also represent the most common type of prodrug, primarily because of the ease with which they are prepared and with which they are hydrolyzed in the body. It's pretty easy to hydrolyze an ester. Ester prodrugs have a variety of different functions, not just rate. For example, consider the structure of the antibiotic agent chloramphenicol. So here's chloramphenicol, and the hydrolysis of it is going backwards, but going, can you make the prodrug? So this is the drug that we actually want. That's the active form as drawn. But this compound is able to dissolve in the mouth where it can interact with our taste receptors. So producing a really terrible bitter taste. So this property isn't very good, especially if you want kids to try it. Getting it down the hatch in your mouth is not so easy if you need the kid to take chloramphenicol. So what you do is you avoid this by converting the one of the alcohols to the ester. And it only does it with one. Can you imagine which one it reacts with? Is it going to react with the alcohol shown in blue or the alcohol shown in green? Which one do you think it reacts with? Well, the one in blue is a secondary alcohol. The one in green is a primary alcohol. And purely based on steric hindrance, the primary alcohol is more available. And so you can actually take the active form of chloramphenicol, do an in, up, down, out with the chlorine. The chlorine is going to be your leaving group. And you end up with this, CH214, CH3. So there's 14 of those. Yikes, it's a big group. But it esterifies the alcohol that's primary. And then because it's not an OH and doesn't have the hydrogen bonding interactions, it doesn't have that same bitter flavor. Esters, if you think about it, if esters are responsible for the nice aromas we think about, like bananas and pineapples and raspberries and all of those smells that we smell are aromatic, I shouldn't use the word aromatic, are really nice smelling esters. And so that is also what's responsible for those tastes. Therefore, we're making it taste a lot better having an ester there rather than the OH. All right, what about esters with amines? Again, we can heat these up and avoid using acid or base catalysis, but I'm actually going to show you, I typically run these with a little bit of acid in here just to get things moving a little bit easier. But understand that you don't have to have a strong acid or base because, again, amines are basic by nature. But I like to run these with a little bit of acid. It's not necessary, but it does work better. So we can do acid-base catalysis, activating the carbonyl. Remind ourselves we're going to drive off. Actually, you know what? I'm going to make this a methyl. I like to give you a real example. So we're driving the methoxy off. We're driving the nitrogen on. So if I reacted it with ammonia, the nitrogen is what I'm driving on. So we're going to do an in-up reaction. In and up. Driving off the methoxy, driving on the ammonia. We're going to do a proton shift. driving on the nitrogen, driving off the oxygen, and down and out. We drove methanol off. We drove the nitrogen on. We are done. We just have to work it up under basic conditions to take off the extra proton, and we arrive at the amide. Done. In, up, down, out. In, up, down, out. Are you guys bored with in, up, down, out yet? All right. Next, esters and a Grignard. This one's a review. We've actually already done this flashcard. You can dig this one back out. I don't need an acid to catalyze this. Why? Because I'm using a strong nucleophile. I'll use a very different ester. Here's an ester. I'll use, I don't know, ethyl magnesium chloride. There's my Grignard reagent. The carbon is strongly negative, so I don't need to activate it to a positive because I've already got a strong negative. I'm also using my unidirectional arrows because I'm adding a carbon, and carbons don't pop back off, so this is not reversible. Once I do the in-up reaction, it can't reverse itself to give the starting material again. I just pushed the carbon on. I'm going to pull off the oxygen. Down, out is next. Down, and the only thing to push out is the yellow oxygen. And then you ask yourself, I started with an ester. I am at this point, after adding an ethyl, I am now at a ketone. So let's just say I had 10 of these esters and I had 10 of these Grignards. I used up one, so I have 9 left. I used up one and I have 9 left. So I have 9 esters, 9 Grignards left. I've got 1 ketone. Okay, 1 ketone and 9 esters, right? Who's the next 9 ethyl magnesium chlorides going to react with? Let me remind you, we've been starting every slide with the reactivity table right up at the top here. Ketones are more reactive than esters, right? So if ketones are more reactive than esters, that means that the next equivalent of ethyl magnesium chloride is going to react with my product before it even touches my starting material. This is exactly why you can't stop at the ketone. So when you're doing Grignards with esters, you just got to keep going because ketones are even more reactive than what you started with. There's no way to really stop efficiently at the ketone for this reaction. So just keep going. The negative carbon goes in and up. We have now added 2 ethyls to our system, and we're stuck. The O- cannot come back down and out. I mean, at this point, we're just doing ketone chemistry from last chapter. Ketones react with Grignards, and there you go, right? From that point, we just are repeating old chemistry. We're stuck, so we just have to work it up with an acid, and we're done. What's next? Reductions. What happens if we have an ester and we do a reduction with lithium aluminum hydride? This is sort of a review as well. Let's start with, I'm going to change things up. Oh my God, I'm going to get crazy. Just to be crazy, I'm going to put the ester drawn on the other side. I'm using unidirectional arrows. Why? Because lithium aluminum hydride is adding hydrides, H minuses. H minuses don't come back off. This is like saying I have 4 equivalents of H minus. So A, you can't stop the train. One molecule delivers a shot of 4 H minuses, and it's going to do an in, up, down, out reaction, but irreversibly. In and up. I'm putting an H minus on. Ultimately, the ester is going to pop off. I can do my down and out. I'm under strongly negative conditions. So notice I don't do these proton shifts. It's okay to throw out a strong base under strongly negative conditions. That was my down out. And oh look, I have an aldehyde. Aldehydes are more reactive than esters. And I have a ton of H minuses anyway, so just keep going. It's kind of like the Grignard. Aldehydes are very susceptible to 1,2 additions with a hydride. We saw that in the aldehyde chapter. Can't stop this train. So driving another hydrogen on. We've then driven 2 hydrogens on. We are done. I can't come down and out anymore because I've got nothing but hydrogen, hydrogen, carbon. So I just work it up under acidic conditions, and I'm done. In, up, down, out, in, up, down, out. Okay. Is there a way to stop at the aldehyde like we saw with the acid chloride? And there is. And we have a very special reaction to do that. Now, I want you to recall something. Recall that for the acid chlorides, we used a very special reagent that only had 1 H minus. And in doing that, we could stop at the aldehyde. Now, I need to remind you, right, that acid chlorides are way more reactive than aldehydes. So therefore, if I add 1 equivalent, it's okay because I'm creating something that's less reactive than my starting material. So the next equivalent will definitely react with the acid chloride. So I'm not really in much danger here. Okay, so keep this in mind. I need to use a very different reagent when I'm doing an ester and stopping at the aldehyde. That is this new reagent called dibal. Dibal is diisobutyl, that's what I just drew, diisobutyl aluminum hydride. What do you notice as opposed to the other hydride sources we've been using? This one is certainly different. Do you notice anything different about it compared to the other hydride sources we've been using? Take a look at lithium aluminum hydride right here and right over the arrow, the first arrow. What's different about it? Well, aluminum is in group 3, and this aluminum only has 3 bonds around it. So this is not an ionic salt like lithium aluminum hydride is. So there's 2 things to note here. The first thing is that there's only 1 H minus. Okay, so there's only 1 hydrogen for us to put on. So that's good. But the second thing is that the aluminum has 3 bonds. Now remember, aluminum is very fickle. It thinks it wants an octet, and so it's very susceptible to behaving like a Lewis acid. We saw this in the aromatic chapter, right? When we had, Friedel-Crafts alkylation. You'd react it with aluminum trichloride. The chlorine would react, this would be a Lewis acid, and you would end up with this adduct here. The aluminum is like, whoa, but it's very accepting of electrons, so it acts as a Lewis acid. So not only are we only giving it 1 H to do chemistry with, because we want to control it, we only want it to add once, we also are not, we're allowing the aluminum to invite another bond, to be a Lewis acid. So this is going to do a couple things for us. It's going to activate our carbonyl, and it's going to hold tight until we work things up. So here's how it happens. Let's do Lewis acid, Lewis base chemistry plus 1,2 addition. The oxygen of the carbonyl, instead of being reacted with an H plus acid, it's reacting with the aluminum as a Lewis acid. Lewis acid, Lewis base chemistry. I don't want to draw those butyl groups, so I'm just going to write R. 2 big R groups. Now that the oxygen has reacted with the aluminum, the oxygen is now positive, so the carbonyl is activated, and the aluminum is now negative because it's got its octet now. It got the octet it thought it wanted, but now it's freaking out because it's got a negative charge on it. And so we've got this intramolecular situation where the carbonyl is activated, it wants a nucleophile, and the aluminum would love to spit something out. So here we go. The aluminum is like, hey, hydride, get out of here. So this is where your H minus is coming in. And the carbonyl is like, yes, please attack me. I'm activated and ready to go. So here's our intramolecular in-up reaction. Just got to see it for what it is. It really is a 1,2 addition. Now here is where things are kind of cool. I'm highlighting to show you that, I'm highlighting to show you that things are pretty much how we've been doing them, right? We did, instead of regular Bronsted-Lowry acid-base chemistry, the aluminum acted like our acid catalyst, activating the carbonyl, but then intramolecularly delivering the nucleophile. And now we're at this crazy system here. This is our intermediate. And I will tell you here that aluminum oxygen bonds are very strong. Okay, so these aluminum oxygen bonds, this is not going to let go for a down out. Right now, the aluminum's holding on, right? The aluminum's happy, it's got its 3 bonds, the oxygen's got its 2 bonds. At this point, this is a pretty stable intermediate. This is an aluminum alkoxide intermediate. and it's soluble typically in water. Ugh. So this thing's hanging out in the water layer. You need to, in order for the down out to happen, you have got to entice the heck out of it for the down out to happen. And this is where it's weird. The down out actually happens during the workup phase, what we call the workup. You add a bunch of salts, sodium OR minus groups. So you need a lot of OR minuses. And effectively, the down out is sort of a SN2 down out, if you will. You're trying to kind of entice the aluminum to make more oxygen bonds and let go through equilibrium with the one that it has. So you can make this in equilibrium. So what's happening is that you dump in a ton, and I mean a lot, because you want the equilibrium to shift towards the product. You dump in a ton of OR salts in the workup, in water, and you shake it overnight. I mean, you go home and you let this vigorously shake overnight, and these salts, the oxygen will react with the aluminum, and hopefully it will exchange out the other oxygen, right? So if you say, here, take this oxygen and let the other one go, if it does that, then the down out is free to occur. The down and out can happen. And look at what you're generating, just more OR negative salts. But in the process, this is what's really cool. You've just generated more OR negative salts. You've gotten your aldehyde. Your aldehyde is now soluble in the organic layer because it's not ionic anymore. It's not like a salt. And so this is where you see a partition. The workup, since you ran the reaction in an organic solvent, I don't know, hexanes or dichloromethane or something. And then when you get to the workup stage, the workup is aqueous. There's lots of water and these salts. Once this collapses, once your intermediate collapses to do the down out, because the down out is only going to happen during the workup. You're not going to reduce it with the hydride if your molecule stays stuck at this position. So it's going to stay like that until you come along, work it up vigorously, and then as it's worked up and collapses to give you the aldehyde partitions to the other layer because it's now soluble in the organic phase and not in the aqueous phase. And it's safe in the organic phase because there's no more H minuses available there. So this is a tricky way to stop at the aldehyde. And you have to use this special reagent called dibal. Looks trickier than it actually is, but if you look at the flow, the only difference is that the down out only happens in the workup stage. We have now done most of this schematic, if you kind of trace it all out. We just have a few more to do, and they are surrounding the amide. So that'll be in the next set of notes.